Welcome everybody, bienvenue à Québec. I've been living in Quebec most of my life and I'm glad to be back. I'm going to introduce you to maybe not an introduction for everybody, but to the in-transit measuring system. There's two main ways to do that. When this thing doesn't work, so I want to do a little history of these methods. I will use patent example. I'm not quoted any paper because I decided to do it this way. And then I'm going to introduce the different systems, especially how do we measure the slump, because that's what most people are interested in, and also what kind of other measurement these systems can deliver. And I will introduce also the more global system where this in-transit measurement system is connected to other systems like GPS and the cloud and the batching plant. So I'm going to give you some example of this. Just for what you see on your right side is a in-drum sensor that I'm going to discuss more later. Why these sensors? Why these in-transit measurement system? Because the ready-mix producer is responsible for the final quality of a product, despite having very little control over the quality after the product leaves the plant. So we put a lot of effort in having very good mix design, control the material, and then when it leaves the plant, it's in the hand of the driver. He can add water. We cannot really check him most of the time, so we're at the mercy of their behavior. If they're not paid last week, maybe you'll have bad concrete. So actual quality process after batching don't really help assure quality. It will help you to get rejected truck, but it doesn't really help to find out what was wrong, or because you have very little information of what happened after it leaves the plant. So people have been looking to uncover the delivery back. I call it black hole, is the time between it leave the plant and it arrive at the site where you can do your first quality control measurement. And they have tried to do that for more than 90 years. So my first patent I'm going to present to you was made in 1929, so which is 90 years ago. And it was a system made with lever and spring. And basically you were able to measure the slump by having a sensor directly in contact with the concrete. We call that the direct method, where the measurement of either force or pressure applied directly on a member immersed in concrete is used to obtain certain characteristic. And for many, many years, the only characteristic that people were able to measure was an estimation of the slump, because we don't measure the slump, we try to estimate it through an indirect method. So a little bit later, another guy, I will not mention any name because I'm really bad with names, used a similar device, but it has a recording capacity, so it was called a mixometer. I don't think they are in use anymore, but I will skip a little some patents because there were many patents in that field. But in 1944, another guy described a sensor that would be mounted on a turning drum. The other was on a fixed drum. So this is like a in-between step, so you can go to a transit mixer. Basically, the main drawback is that you have to read the slump while the drum is turning, so you have to really follow the drum because there's no way at that time to transfer the data electronically like we're doing. So a few years later, that's another method, a completely different concept, is that people were using the indirect method where measurement of power or energy that is required to turn the drum or the mixer is used to obtain certain characteristics. So initially it was for slump. So you might have been in contact with a pressure gauge that would either measure the pressure and the driver has to guess what is the slump, or some sort of meter that will indicate the slump, but it's based on the hydraulic pressure required to turn the drum. there were also some work done by people to measure the rheological property, turning the drum at different speed and then trying to relate the pressure and drum speed with rheological parameter. In 1968, another guy devised a quite ingenious system to measure the torque with a chain and some readout so that you can measure the slump with a graduate gauge that was directly measuring the slump. The main advantage of this one is that you didn't have to turn your head and follow the drum turning. So in 75, there was a similar idea. This was not only patented, but it was used quite extensively, well, everything's relative, in England. And this device has the same disadvantage. You have to read while the drum is turning. So it took a few years for a new system that would be, I would say, more evolved, that were able to get the slump or other parameter in a, I would say, more sophisticated manner, but also maybe more precise. So in 1990, it's pretty much similar to what was described in 57. It's again the pressure that is an indication of the flow resistance. It's similar to what we are using now, and that's what I will present, but there was no way to, sorry, I'm a bit lost here, so. Anyway, what I want to present here is that there was many attempts to do this thing, and very few were successful until 2002, where construction equipment parts used the hydraulic pressure with a better calibration to give the slump. And this calibration would take count of the volume of the material inside the drum, not only the pressure, because obviously if you have less material in the drum, it will require less pressure, and it's not necessarily an indication that the concrete is more fluid inside. So your calibration needs to be to take more parameter in account. So, and with the year going, people were able to measure different things than the slump. For example, in 1998, a guy from Quebec used a turn count to calculate what amount of concrete is left in the drum after you start unloading the concrete. So if you know the initial volume of concrete, and then you know that every turn you 1/4 of a cubic meter of concrete is going out, then you know that after 2 turns, provided that you have done a few turns to bring the concrete to the end of the drum, then you know how much concrete is going out. So, and there were many other development, and another guy has developed the sensor I'm going to discuss now, which is me, which was able also to measure the drum speed, the temperature. So it was like an integrated sensor that can do more measurement. And obviously after that, there were so many patents after the year 2000 that I'm not going to describe them all. But in 2010, and I don't know when it will be finished, but the ACI Committee 238, which is sponsoring this technical presentation, prepare a technical note, which now will not be a technical note, will be another document, which is titled, or was aimed to be titled, Technical Note on Automatic Methods to Measure and Control Concrete Workability in Transit Mixer. So not only we are able to measure some parameter while in transit, but some companies have developed system to adjust some parameter, mainly the slump now, but I'm sure in the future we might be able to adjust temperature by adding liquid nitrogen or something like that. But at this time, this committee has defined 2 methods, and they are the indirect method and the direct method, which I try to introduce you through this patent review. So basically, the first one is an indirect method where you are measuring the hydraulic pressure in the drum hydraulic system when the drum rotates to evaluate the slump. Some people have tried to evaluate, as I said, rheological properties with that. And also the direct method where you have a member which is in direct contact with the concrete and where the sensor measures the pressure while the drum is turning. Of course, there are many parameters that must be taken into account to do that, the drum speed, the volume of concrete, etc. But the indirect method has many limitations, but has been around for a long time. And with the experience, it was used as the basis for the slump adjustment method while in transit. So these automatic methods, they all have many advantages, and most of them, actually, both direct and indirect, they give you real-time measurement. And they do it continuously, so there's not a slump measure at the plant and then one at the site. You have this thing done continuously, and there's no need for sampling, so you don't lose concrete while doing these measurements. And it's done without human error, no influence, because you get the result on a display. Of course, you can have just hydraulic gauge, and the driver experience is needed to see that a 3,000 PSI concrete with 8 cubic meter is this much slump. But people have been moving away from just hydraulic gauges, so now you have display of the workability on a digital screen, so it's much easier. And there's no need for training. It's not completely true, because you still have to train people to how to operate the drum so you get the right measurement. But it's very easy compared to teaching a guy how to read the slump from dumping some concrete or just hearing in the drum because he cannot see inside because of the fog in winter. So, and it's much safer because he doesn't have to climb the ladder that many times. So they all have all these advantages, which is significant only for that, but they are much more advantageous when they are integrated with other systems. So if you add, for example, a flow meter to this system, then you can follow how much water is added, when, and for what purpose. Is it for washing because the drum is empty, or is it to adjust the slump in the middle of a pour? So you have all these data available to you. And you can, with the GPS system, you can also know where the concrete has been delivered. So maybe the guy has an 8 cubic meter yard. He went to his friend, dumped 2 cubic meter for the floor, and then he go on a large pour, and nobody noticed that there was only 6 cubic meter left in that truck. So with the GPS, you know not only when things have happened, but where. So this is a big advantage. So now, for Common Alkon, they have used a sensor, which is the direct method, to create a system that is called Common Assurance. And basically, there's 3 main components to the basic system, which is basically the probe itself that can measure the status of the concrete inside and its volume, and a display that will allow the driver to see on a digital screen what is the value of different parameters. And there is a solar panel that keeps the system working, because you don't want to connect this system every night to recharge it, because it needs some power to operate. So the probe looks like that. It's about this long. And the display could display different things, but mainly we're displaying the slump. Now the temperature is blackout because some people don't want to show it, so we have different label. And the volume of concrete inside the truck, plus for some, when some parameters are fixed, we can get the yield stress and the viscosity. Now, this installation is not so complicated. You have to make a hole through the drum. You weld a stainless steel plate, and then you just have to bolt the different component. And then the probe itself will be covered by the solar panel. So Nobody knows it's there, but it's working. And that task takes about an hour and a half. And then the system can be expanded by having a GPS system. In that case, you will need some GPS tracker, which could be inside the tablet that would be mounted in the cab, so you could see, you could use it as an additional display that can be brought outside or not. But you need also some connecting boxes, which we call an input-output box, I/O box. And then this tablet is connected through the cloud, which the system will store the data. And this cloud can also be connected to your QC system, your batching plant system, and your dispatch system. So the data exchange could be both ways, directly from the plant to the probe, and to the probe to the plant, or to the dispatch, or to the QC, and you can see all these data in real time live. So that's quite handy. So there are many screens that the driver can go through to see different things, and you can set alarms also to warn that, hey, you are above the expected water cement ratio, so don't add more water. Sorry, I'm finished? Okay, so, 10 minutes, good. Thank you. So, how this sensor works? Basically, they are measuring 4 basic parameters, which is the time, the angle or the position of the probe, the temperature, and the lateral pressure when the probe is in the concrete. So, but you can combine these different inputs, and then an easy one is the drum speed. If you have the angle and the time, so you know I've moved 10 degrees within 10 seconds, so you know what speed is the drum. The same thing, you can measure the pressure at the bottom of the drum, and then from that pressure, you can estimate what's the slump. So there's many, many, many steps we can do, and I will show you how do we estimate the slump. So basically, you take a concrete mix with a stiff, low slump, and then you measure the bottom pressure and you record both. Then you add some water and you record again. You turn the drum, you mix it, and then you record the new pressure and the new slump. And then you have a series of points which are pressure and slump, and that's your calibration. And then you just input that in a table, and then whatever is the pressure, the system interpolate and get you the slump. So it's quite easy. The calibration works for almost every single mix, except when your water cement ratio become low, then you have to shift a little bit the calibration. And also for the very, very low slump, below 2 inches, that system might not be the best. The hydraulic pressure is maybe more precise for the very low slump. But anyway, when you have 2-inch slump, it cannot be 5-inch, so you know it's low slump. Now, how do we measure the volume inside this? So the volume, there is a measurement. What is the actual volume inside the drum when I don't know anything? So basically, how it's done is that when the drum turns at the, okay. If the sensor is on this axis here and I cut the drum, so you can see the probe when it's turning. You can define an entry angle where you start seeing some pressure. And then when that pressure is gone, then you know you're out of the concrete. So basically, the angle travel within the drum over a full turn give you a ratio. So it will be between 1 for a very full drum and 0.5 for half a drum. And then you just, again, build a table with this much concrete, this ratio, and then you have a table of ratio versus volume. And then when you don't know the volume, the system turns, it measures the ratio, and then it estimates the volume. That's what we call the measured volume. But you can also calculate what's left in the drum when you are discharging by having this amount of concrete going out every turn. So that's what we call calculated volume. Of course, if you are linked with your batching plant, you know exactly how much concrete was put initially. So then your calculation is more precise because you have the right number to start with. So obviously we can measure temperature, and this can be used to detect water addition if the guy wants to add water but not using his own water, so it doesn't show on the flow meter. If you add like water from outside, you can detect it. You will see a change in temperature. Unless the temperature of the concrete and the water is exactly the same, you will see a small change in temperature. And obviously, you will see a change in slump if there is concrete. And the system can determine the status of your delivery. Are you underloading, mixing? Are you unloading? Are you washing? So all these status can be defined by the system. It could also measure the rheological property, but then you need to train the driver a little bit to turn the drum at different speed. And then with different speed and different pressure, you can get some sort of rheological parameter. And the probe send all this information to the display, which relay it to the I/O box, and then relay it to the tablet, and then relay it to the cloud, and then you relay it to wherever you want. You can see it on your phone also if you need. It gives you a lot of traceability. This is an example in 2014 in Japan, and you can see every single, you can see different load and different parameter that could be changed. In that case, you have the volume in yellow, you have the slump in orange, you have the temperature in blue, and you have the drum speed in green, and the pressure in dark green. Now, you can also just select a few one, and then here you will have the slump going down with time. Here it's one single load. You can isolate one load to see if how that delivery went. So here you will have the initial volume of 5 cubic meter in that case. And then in green, you have the speed. And whenever it's going down like that, it's because it's a negative speed, so it's below zero. So you are unloading. So every time you have negative speed, you can see the volume going down until it's empty. So, and the slump here is measured also in orange. One thing that is very interesting now is that we have the slump history, not only one point at the plant, one point at the job site, but you could have the full history during the delivery. So you can estimate what I call a fresh concrete aging rate, which is the loss of slump per minute. If you go metric, we give it in millimeter per minute, but we can give it in inch per hour. It's not a big conversion to do. In that case, it's 0.7 millimeter per minute, and that can help you to identify mix that are difficult to work with because the aging rate, if it's above 2 or 1.5 millimeter per minute, you might have trouble delivering this concrete to a far site. Here it's an example of admixture addition. So this is the initial slump of the concrete, which is in centimeter. This is in Japan, so it was about like 15 centimeter. So you see the slump going down with time. You have the time here. And then, suddenly the slump is higher, and what happened? So basically, you see here they were mixing, but the temperature has not changed a bit. So that means they have not added water. They have added admixture. And I was there, so I know they have added admixture, so it's easy to say. But in that case, I was not there, and it's a delivery that happened under my supervision when I was in UE. And then there's a small slump increase, and not a big one, but you see the speed of the drum here is very high, so they have been mixing. But I don't know if they have added admixture or water. But since I see that if I change the scale of the temperature, you can see that the divisions are quite small. You can see that the temperature, it went down, because normally it goes up in UE, it's about 40 degrees all the time. So, but here it went down a little bit, so that's suspect. Since they have been mixing and the slump was increased, I know they have added water to this mix. So there's no doubt. The guy denied it, but in the end, he'd give it away. So the conclusion, there's no real conclusion because this is an ongoing development. It's quite recent, and lots of people are working on it, and there would be, I'm sure, a lot more to tell you in the future. But this in-drum assessment started a long time ago. That's the conclusion I want you to retain, is that it's not new. We're working on it, and it's going to go we don't know where. But it's quite recently that many systems have been integrated together, especially with the batching. Verify did it some years ago. They had some batching data that was sent to the system. But this gives us powerful tools now to say that there's no more black hole anymore. We know what we are doing, and we can show people that this is what happened. And now if you want to claim from me, it's going to be more difficult. I'm not the guy who will always be, oh yes, we did a mistake, even if you didn't, as a concrete producer. So thank you very much. I hope I'm on time. Perfect, thank you.
Thank you, Denis, very much. We have time for a couple of questions.
How does your slump measurement correlate with real physical slump cone and thermometers and volume measurement?
It's very good. And some people can't talk more about it because you would expect me to say it's very good anyway. So, but I will let the other to talk about it, but it's very good. That's the only answer I can give you. I have graph, but I don't have time to present it.
So my question is, you have correlated them to come with your correlation?
Oh yeah, for sure. I mean, we know that, you see, normally we're precise within, because we did also comparison. How precise is the slump test versus how precise is the probe? Because we've put many probes on the drum, so each probe would measure something, and you would have different measurement for different probe. And if you look at the coefficient of variation between the measurement of the different probes, it's about 2.7. If you look at the coefficient of variation of the technician, because what I did the first time, I had 5 technicians, they all take samples, and they went away, they did their slump test, and we collect the data. But the coefficient of variation of their result was about 7.5%. And if you look into ASTM, they say that the slump test is a precise test at 7.5%. So we were like 0.1% off of what they say. So the probe is more precise, but it doesn't mean it gives the slump more precisely. It's less variable in what the result is giving. So if I can just go back one graph, you will understand what I mean here. It's here. It's that from turn to turn, if you look here, you see every turn is a measurement. And it's not going like this. It's not going like, so it's quite precise as a measurement because it's not varying a lot. But now, if I don't have the right calibration, I mean, I can get you 100 slump if I just change the number in the table, but this number will still be stable. So the precision of one thing is different than how it correlates, but it correlates well. Yes?
One last question.
I'm sorry for the long answer.
I will be brief.
Yes.
Your probe, it has been my experience that the inside of the drum can be a very bad place. Your picture shows a clean drum, but most of the time there's a lot of development.
Yeah.
How does this probe survive this environment?
That was my biggest concern when my boss asked me can you develop something to go inside? I told him if you can survive 5 seconds inside the drum, I'll do it. But anyway, he didn't do it, but I still do it. No, initially we used normal steel to build the probe, and then it was sticking all the time. But we use stainless, and the concrete doesn't stick much to stainless. So the probe stays clean very well, as long as it's placed properly within the drum. If you place it too much at the back of the drum, it gets dirty. But if you place it in the front of the drum, even if you don't clean it very much between the different, when you put more concrete into it, it's just clean it off. So it's very rare we have problem with. And the second part of your question is how much does it last? So far, in Japan, we just got very recent of probe that have been used for 3 years now. The estimation is they're going to last 55,000 cubic meter in the drum. The previous result we had was 30,000 in the Middle East on many trucks. And on dry batch, we don't have much result, but we have only one producer who we had enough data, and it was about 17,000 cubic meter. So if you consider the life of a drum, it's about the life of a drum, the sensor, so that's it.
All right, let's thank